Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So our next talk is going to be is called Actor-Critic Algorithms for Risk-Sensitive MDPs by Prashant L.A. and Mohammed Ghavamzadeh. And Mohammed's going to give the talk.
So thank you for having me here. I'm currently on leave of absence from INRIA, working at Adobe Research in California, and it's a joint work with our postdoc back in France, Prashant L.A. As the title implies, this talk is about managing risk in sequential decision-making problems. Sequential decision-making under uncertainty arise in everyday life in problems like navigation, process control, finance, and medical diagnosis. And many interesting sequential decision-making problems can be formulated as a reinforcement learning problem in which an agent interacts with a dynamic, stochastic, and incompletely known environment with the goal of learning an action selection strategy that we would like to call it a policy in order to optimize some measure of its long-term performance. This interaction between the agent and the environment is often modeled as a Markov decision process, or MDP, which is a 5-tuple in which X is a set of states, A is the set of actions, the capital R is the reward random variable of taking action A in state X, whose expectation is the little r, and P is the dynamic of the system, which tells us if you take action A in state X, what would be the distribution over the next states, and P0 is the initial distribution of the system. So what's important is policy, and policy is a mapping that looks at the system, what has happened in the system from the beginning up to now, and try to tell us what to do and which action to take. Of course, we are more comfortable to work with and are interested in a stationary Markovian policies that are mappings from states to actions or distributions over actions. So one of the common criteria in sequential decision-making is discounted optimality or discounted reward MDPs. So let's go to the system. At each time, you are in a state X, and you have a strategy mu, and then using this strategy, you interact with the system, and you generate a trajectory of the system, and along this trajectory, you observe rewards, and then you put these rewards together, weighted by the discount factor to keep things bounded, and then you have a quantity, which is called the return of this policy at state X, and if there is any intrinsic randomness in the system, this quantity is a random variable. Therefore, in a standard risk neutral, the objective is to find a strategy that maximizes the expectation of this random quantity, which we call it the value function. Of course, weighted by the initial state of the system. For simplifying the notation, I assume that the system has only one initial state X naught, and therefore the risk neutral is trying to find a policy that maximizes the value function at X naught. I want to have a footnote here that I'm using sum in this talk, but you can replace all the sums with integrals, and everything is going to go through. So we are not restricted to discrete systems here. Another popular optimality criteria is the average reward optimality. An average reward of a policy is the reward per step of following that policy, which can be also written as the multiplication of the stationary distribution of the system over state action pairs times the reward function. And again, here the risk neutral or standard objective is to find a strategy that maximizes the reward per step. From the literature, we know that for both discounted and average reward, these optimization problems have a stationary Markov and even deterministic policy, and we have a repertoire of algorithms in order to exactly or approximately find these policies, both in average and discounted setting. Okay, so now, in many problems, we may want to go one step ahead, because look at this. So let's think about the discounted case. Let's imagine that you learn a policy, find the optimal policy. Now you go to the world, and you have one life to live, and you execute your policy, and this is the result that you get, is the return. If this policy has a lot of deviation, and this value deviate around the expectation, it may not be desirable in some problems. And this is when we would like to control this variation. So when we talk about risk, you immediately think about finance, investment, or sometimes about Bernie Madoff. But in many other sequential decision-making problems, risk is important. For example, you may decide to deviate from your shortest path in order to avoid a dangerous highway, or you may want to lose in terms of the performance of your system in order to control its variability because it might be dangerous for the rest of your system. So therefore, we are looking at a criteria that penalizes this variability induced by a policy because it might be undesirable for us. Or in other words, we are trying to minimize some measure of risk as well as maximizing our standard optimization criteria that we were dealing with. So now, what is a risk-sensitive criteria? We have some work in the literature. We have expected exponential utility, which has direct connection with mean variance trade-off. A very natural and well-studied set of criteria are the variance-related measures that have been very well studied. And now people are looking at percentile optimization and percentile control, but the open and important question is to construct a conceptually meaningful risk criteria, which at the same time is computationally tractable. That optimization problem is nice. Unfortunately, all the results coming in this front are not very good, from the early work by Sobel and Filar to very recent work in our community by Shaimanur and John Tesiklis at ICML 2011. And when I say bad news, which means that the solution to the risk-sensitive criteria may not be a stationary Markovian policy that we like, or calculating it might be something hard. Okay? So now, working on this and basically trying to restrict ourselves to different set of policies and trying to approximate them has a long history in operation research, much less work in the reinforcement learning and machine learning community, and what discriminates us with operation research is in operation research, they often assume that they know the dynamic of the system, while in machine learning, we would like to consider the case that all the information that we have from the system is from the samples that we obtain by interacting with the system. Some results in risk-sensitive RL are the work by Vivek Burkar on expected exponential utility, and a recent work from the Shaimanur's group that they look at the several variance-related measures similar to what we do in this work, but they restrict themselves to a stochastic shortest path problem and to policy gradient methods. So the contribution of this work is we look at both discounted and average reward MDPs, so more general than their work. We define for each case, we define a measure of variability for a policy first, which in turn induces a set of variance-related risk-sensitive criteria. So here we are restricted in this work to various variance-related risk criteria. For these criteria, we propose actor-critic type of algorithms to optimize the risk-sensitive criteria. For each algorithm, we establish the asymptotic convergence of the algorithm. I'm not going to show any proof and talk about the convergence in this talk, but I would be happy to take questions at the post there. But only mention that asymptotic convergence that we show that we converge to the local saddle point of a performance measure, and saddle point comes from the policy parameters and the Lagrange multiplier. And then we demonstrate the usefulness of our algorithm using a traffic signal control problem. For those of you who may not be familiar with actor-critic is a very elegant, naturally inspired reinforcement learning algorithm which works based on two components. One component is called actor, which is a class of parameterized stochastic policies and is in charge of control and exploration of the system, and tries to improve the policy by tuning the policy parameters in the direction of a gradient of a performance measure. Critic, the other component, at each time tries to estimate the value function of the current policy, so it's a predictor, and passes this to actor and say, okay, use it to estimate your gradient and update your policy parameters. So up to here, I want to deliver the main message that what we are doing in this work. Now I talk a little bit more technical. Let's look at the discounted reward setting. The random variable is the return. In risk neutral, people look at the expectation of this random variable, try to optimize that. The first question is, what is the measure of variability? The measure of variability that we consider here is one of the nicest, more meaningful, but harder to deal with in terms of mathematically and being tractable, which is the variance of this quantity. So the measure of variability is the variance of this quantity. If you want to remember any notation from this slide, is this U is the expectation of return square. So I call it the square value function. So if v is the value function, u is the square value function. So now, any combination of these is this mean and variance, any meaningful combination of this is a risk criteria that our algorithms can handle. For example, maximizing the mean subject to variance to be bounded by alpha, or the Sharpe ratio, which is used in finance a lot, which is the mean divided by the standard deviation. So our algorithm can handle any of them. So I just focus on one of these cases, which is maximizing the expectation subject to variance to be bounded. So we use the Lagrange relaxation, change the constraint optimization to unconstrained optimization. And of course, one needs to evaluate the gradient of this L with respect to both theta and lambda, descent in theta, ascent in lambda, and we are fine. The gradient with respect to lambda is fine. It's easy to calculate. The gradient with respect to theta requires calculating the gradient of the value function at x naught, at the initial state, and the square value function. So in this equation, the only thing that is important is this pi gamma and pi tilde gamma are the gamma and gamma square discounted visiting state distribution of the Markov decision process induced by theta. So now, for those of you who are familiar with actor critic, in risk neutral, we only have the first gradient, and we can estimate this gradient with one trajectory of the system. Unfortunately, right now, because of two reasons, one, we have these two different sampling distribution, pi and pi tilde, and second, in order to estimate the gradient of a square value function, we need to estimate the gradient of value function at every state. Because of these two problems, we cannot estimate the gradients with one trajectory of the system. And what we do is we look at these simultaneous perturbation methods that are very elegant techniques to estimate the gradient of a function using two simulated trajectories of the system, one using the current parameter, theta, the other one using the perturbed parameter, theta plus beta delta. Beta is a scalar. Delta is a vector of independent random variables. If these random variables are Rademacher, it's simultaneous perturbation stochastic approximation SPSA. And if it's Gaussian, is a smoothed functional. And these are the way that they estimate the gradient. The elegancy of these methods comes from the fact that no matter what is the size of the gradient, only two trajectory is enough to estimate the gradient. Okay, so this is the structure of the algorithm. This is an incremental algorithm. We generate two trajectories. Trajectory one using the running parameter of the system theta. Trajectory two using the perturbed parameter of the system. And then we have the critic, which estimates now both value function and square value function, and passes these estimates to actor to estimate the gradient and update both the policy parameters and the Lagrange multiplier. So I ignore these formulas. The only thing that I want to emphasize, this is the formulation in the critic. So for critic, now we need a method for policy evaluation. As Peter explained, temporal difference learning, TD, is a method that we use to evaluate a value function, but we don't know whether this machinery works for the variance-related quantity, the U. So what we were working on for both discounted and average, but the Shai-Manor's group published it at ICML 2013, is to show that TD actually works for the variance-related quantities. So they showed it for the stochastic shortest path. We needed for discounted and average. We basically extended it. But this by itself was a contribution that showed that the critic by itself works for the variance-related quantities. And then this is the actor, and updates the policy parameters and the Lagrange multiplier. What is important is, in order for us to guarantee the convergence of these algorithms, the three step sizes, the zeta 3, the step size for critic, zeta 2, step size for policy parameter, and zeta 1, the step size for Lagrange multiplier, should be in a way that the step size for critic is on the fastest time scale, the zeta for theta, the policy parameters, on the intermediate time scale, and the other one on the slowest time scale. Then we can converge, we can guarantee the convergence of this algorithm. So it's a 3-time scale stochastic approximation algorithm. What we don't like about this is we would like to estimate everything with one single trajectory, which here is not possible, so we need a simulator of the system. The good news is, if we fix the Lagrange multiplier and don't optimize for the Lagrange multiplier, we can estimate the gradient in one trajectory and have a 2-time scale stochastic approximation. So basically, we have to choose 10 different Lagrange multiplier, optimize for each, choose the best. So for the average reward, I go very fast. The situation is very similar. The only thing that is important is what is the measure of variability for average reward. So we want to optimize for average. The measure of variability that we consider is how much the immediate reward deviates around the average. That's the measure of variability, which is called the long-run variance. So again, any combination of this rho and lambda can be optimized by our algorithm. So again, one notation that you should remember from this slide is eta. Rho is the average reward. Eta is the average square reward. And we need to deal with this quantity. Again, for the case of maximizing average, do constraint on variance to be bounded. We need to calculate the gradients. Now the gradients requires calculating the gradient of the average and average square. But the good news is in the average reward, we can estimate these gradients with one single trajectory of the system. Good news. And this is the structure of the algorithm. And so we estimate the value and the average and average square. We have the TD algorithm. We have the critic, which calculates those, and actor update. So again, here, the zeta 4 and zeta 3 are on the same time scale, the fast time scale, zeta 2 intermediate, and zeta 1 is slow, so it's a 3-time scale stochastic approximation. If we want to fix the Lagrange multiplier, don't optimize for it, it's a 2-time scale stochastic approximation. So experimental result, we apply this to a traffic signal control problem that cars are coming with a Poisson distribution, and we want to, so far I talked about reward and maximization. This experiment is cost and minimization, so the lower is better. So we want to minimize the number of cars in the system, which indirectly minimizes the delay of the cars in the system. And so we formulated this problem at both average reward and discounted. I just showed the result for average, but the same for discounted. The way that you should read this result is, look at the one on the left. So we run an algorithm, we learn a policy, we execute this policy several times, and each time we calculate the average reward or the return. So we have a number of these values. We calculate its mean and variance. We represent it as Gaussian. So nothing is Gaussian here. Gaussian has been used just for representation. As you can see, the fat Gaussian is the risk-neutral algorithm. And its mean is smaller, so it's better. But it's when we go for risk sensitive, we lose a little bit in terms of mean, but we get a thinner algorithm and less variance. And the one on the right side is the average junction waiting time that for both algorithms. So at the beginning, the waiting is 0, but the cars are coming. If we don't have a good control, these graphs should shoot to infinity. But the control basically flatten it out, and you can see that the performance of the risk sensitive is a little bit worse than the performance of the risk neutral. But we reduce the variance. So I just wrap up here, and future work is looking at more interesting and sophisticated risk sensitive criteria, and of course, looking at finite time bounds for these algorithms. But unfortunately, we don't have finite time bounds even for risk neutral actor critic methods. So it might be a little bit orthogonal. So thank you for attention. I'm ready for question, and we are hiring both interns and researchers at Adobe Research. If you're interested to know about it, I'll be happy to talk to you. Thank you. Sorry.
We have time for some questions, but those who are going to do the spotlight presentations immediately after this talk, would you please come up and stand behind on this side? Thank you. So Nanda, you had it.
Thank you. My question has to do with meta control, what Peter alluded to in his last slide. It seems to me that in going from a 3-time stochastic approximation to a 2-time one, you decided to use a fixed grid for one of the parameters. Now that's, one could think of doing much smarter control there. Because if you're going to be using a grid, you should use, say, Bayesian optimization or use contextual bandits to actually select the best parameters. Moreover, SPSA has a lot of tuning parameters which are actually hard to tune in practice. So what would you think about having a meta policy that is based, say, on contextual bandits that would allow you to tune all these extra parameters? Would it behave well?
I haven't thought about this. That's a good point. I honestly haven't thought about controlling, having basically a meta control separate from, for the Lagrange multiplier separate than the policy parameter. I need to think about it. But definitely, that's undesirable because we remove one of the optimization criteria and just look at the grid. But we make the algorithm more desirable for reinforcement learning, that we like to estimate everything in one trajectory. We don't like to have simulator or anything. But that's a good point. I need to think about it. I honestly haven't thought about this point, but might be. Have you seen such a thing that in optimization they separate the Lagrange multiplier from the rest of the optimization criteria, have like a hierarchical type of way, or no? It's just okay. You can.
Yeah, I have a small question regarding the initial performance of your approach. So in a risk-sensitive environment, it's usually very difficult to actually apply something that does online learning. And I just have a question, how you actually solve that problem. Like, if you go to a traffic light problem, it's not that big of a deal if the performance at the beginning is not that good. Excuse me. But if you think about a more sophisticated problem where you actually risk running a robot or damaging something, it might be very hard to actually apply your approach right now. I don't know. Can you comment on that?
I don't see why the method should be more dangerous if you want to apply it to because whenever we have exploration, roboticists don't like us. But I don't see how the risk sensitive might be more dangerous or than the risk neutral. At the beginning, yes, because we have a lot of exploration and our policies are naive, then it might be dangerous no matter is what. But the goal here is after you learn your strategy and I say, okay, you have one life to live and go execute it in the real world, you don't want to deviate too much. Maybe it's your unlucky day, but you still want to be, at least don't hurt your system or damage it. So it's after the fact. During the case, I don't see any difference between the two cases. We can talk later, but that's...
Okay, let's thank the speaker again.
Thank you.